Welcome back to Operating Systems Crashcast. I'm Victor, and today we're wrapping up our chapter on deadlocks with a comprehensive summary. Sheila, are you ready to dive in?
Absolutely, Victor. This chapter has been quite a journey through the intricacies of deadlocks in operating systems. Let's start by reminding our listeners what a deadlock is and why it's such a critical concept.
Great idea, Sheila. A deadlock is a situation where a set of processes are blocked because each process is holding a resource and waiting to acquire a resource held by another process. It's like a traffic gridlock where cars are stuck because each is waiting for the other to move first.
That's a perfect analogy, Victor. Now let's recap the 4 necessary conditions for a deadlock to occur. These are crucial for understanding and preventing deadlocks.
Absolutely. The 4 conditions are mutual exclusion, hold and wait, no preemption, and circular wait. Mutual exclusion means at least one resource must be held in a non-shareable mode. Hold and wait occurs when a process holds at least one resource while waiting to acquire additional resources held by other processes.
Right, and no preemption means resources can't be forcibly taken away from a process. They must be released voluntarily. Finally, circular wait is when there exists a set of waiting processes such that each process is waiting for a resource held by another process in the set. All 4 of these conditions must be present for a deadlock to occur.
Excellent summary, Sheila. Now, let's discuss the different approaches to handling deadlocks. We've covered 4 main strategies in this chapter: prevention, avoidance, detection, and recovery. Each has its own advantages and challenges.
That's right, Victor. Deadlock prevention aims to eliminate at least one of the 4 necessary conditions. For example, we might implement a system where processes request all their resources at once, eliminating the hold and wait condition. However, this can lead to low resource utilization and reduce system throughput.
Good point. Moving on to deadlock avoidance, this approach requires that the system has additional information about which resources a process will request and use during its lifetime. The most famous algorithm for this is the banker's algorithm. It's worth noting that while theoretically sound, it's often impractical in real systems due to its requirements.
Absolutely, Victor. The banker's algorithm is a classic interview topic, so our listeners should definitely be familiar with its concept. Now let's talk about deadlock detection and recovery. Unlike prevention and avoidance, this approach allows the system to enter a deadlock state.
That's correct. In deadlock detection, the system periodically checks for the existence of a deadlock using algorithms like the resource allocation graph. If a deadlock is detected, recovery methods are employed. These can include terminating processes or preempting resources. However, this approach can be costly in terms of system resources.
Indeed, Victor. It's important to note that modern operating systems often use a combination of these strategies. For example, they might use prevention techniques for some resources and detection for others. The choice depends on factors like the nature of the resources, the frequency of deadlocks, and the system's performance requirements.
Excellent point, Sheila. As we wrap up this chapter, I think it's crucial to emphasize that while deadlocks are a theoretical concern, they're also a practical problem in real-world systems. From database transactions to multiprocessing systems, the potential for deadlocks exists in many computing scenarios.
Absolutely, Victor. And that's why understanding these concepts is so important for anyone working with operating systems or concurrent programming. For our listeners preparing for interviews, remember to focus on the 4 conditions necessary for deadlock, the differences between prevention, avoidance, detection, and recovery strategies, and be prepared to discuss algorithms like the banker's algorithm and resource allocation graphs.
Great advice, Sheila. To summarize our key takeaways, deadlocks occur when 4 specific conditions are met simultaneously. We can handle deadlocks through prevention, avoidance, detection, or recovery methods. Each approach has its pros and cons, and the choice depends on the specific system requirements.
Exactly, Victor. And remember, while we often focus on the theoretical aspects, the practical implications of deadlock management are crucial in designing efficient and reliable operating systems and concurrent applications.
Well said, Sheila. That wraps up our chapter on deadlocks. We hope our listeners found this summary helpful. Join us next time as we dive into a new exciting topic in operating systems. Until then, keep exploring and stay curious.
Thanks for listening, everyone. We'll catch you in the next episode of Operating Systems Crashcast.